What formed first in the universe? After the Big Bang, the universe expands and cools. At some point, things start clustering together into galaxies and stars. How? What happened first? The best current theory is that big stars form first, although it's quite controversial, so that's one of the things that we need to look at. But I think people lean now towards the idea of these huge stars, very short-lived, very bright, they collapse and burn and explode in supernova explosions. You get big black holes at their centres, and somehow that translates itself into the galaxies afterwards. So stars before galaxies. Is that true? That's one of the things that we'll hope to do by looking far away, which means looking right back into the distant past.
More than 100 years ago, Albert Einstein came up with many ideas about gravity and space. In Einstein's general theory of relativity, gravity is treated as a phenomenon resulting from the curvature of space-time. This curvature is caused by the presence of mass. Generally, the more mass that is contained within a given volume of space, the greater the curvature of space-time will be at the boundary of its volume. As objects with mass move around in space-time, the curvature changes to reflect the changed locations of those objects.
What Einstein's theory predicted was that mass, the basis of the theory is that mass curves space and time. So that means that if you've got masses that move and things that happen, violent things that happen, you can get ripples in space and time that move out, just like ripples on a pond if you throw a stone into the pond. So these ripples in space and time from violent events will be passing through this room now because there have been very violent events out there in the universe. But they're very, very tiny shifts. But you can measure it using a process called interference. So you can measure very tiny changes in the distances.
Now imagine you have an unstable star orbiting around a more stable partner. If the more stable massive star suddenly collapses to form a black hole, its gravitational pull will cause space to warp, sending gravitational ripples out into the universe. The interesting thing about these waves is that they go through everything. They don't get blocked by dust or galaxies. They squeeze and stretch anything in their path as they pass by. Every massive object that accelerates produces gravitational waves. This includes humans, cars, airplanes, etc. But the masses and accelerations of objects on Earth are far too small to make gravitational waves big enough to detect with our current instruments. To find big enough gravitational waves, we have to look far outside our own solar system. The world's largest gravitational wave observatory, called LIGO, exploits the physical properties of light and space itself to detect and understand the origins of gravitational waves.
Essentially what LIGO is a set of rulers. They're laser rulers, and they're about 4 kilometers long. And there are two sites, one in Seattle, near Seattle in Washington State in the United States, and the other one in Louisiana. So at each end of the United States, so separated by, 2,000 miles, I suppose. And the rulers are at right angles to each other, and they're laser beams. So you're essentially measuring the changes in the distance between mirrors at right angles to each other with a 4 kilometer long laser beam. So very high precision measurements of changes in distances.
The gravitational waves that LIGO detects are caused by some of the most energetic events in the universe: colliding black holes, merging neutron stars, exploding stars, and possibly even the birth of the universe itself. Detecting and analyzing the information carried by gravitational waves is allowing us to observe the universe in a way never before possible, providing astronomers and other scientists with their first glimpses of literally unseeable wonders. 100 years after Einstein came up with the general theory of relativity, scientists detected gravitational waves for the first time. These first gravitational waves happened when two black holes crashed into one another.
1.3 billion years ago, so 1.3 billion light years away, two black holes collided. And those black holes were of order 30 times the mass of the Sun each. They collided together. They outshone the power output of the entire universe for a fraction of a second in that collision. So a huge amount of energy. So they're orbiting around each other, radiating energy away through the gravitational wave, shaking up space and time as they go, and spiraling in. And there's a plot where you see the closing velocity of the black holes, and it's measured in tenths of a second. And you see that, so in 1/10 of a second, the closing velocity goes from 1/3 the speed of light to 2/3 the speed of light. So you imagine accelerating something 30 times the mass of the sun towards the other thing with a change in velocity that's 1/3 the speed of light in 1/10 of a second. And then they merge together, and you get obviously a bang, and space-time shakes. First of all, it's incredible. So many firsts. It's the first time we've seen black holes that large, actually. Huge, 30 times the mass of the sun. It's the first time, I mean, we know that they're in the centre of galaxies, but this is a direct observation of them. Secondly, it's the first time we've seen them collide together. Thirdly, it's the detection of gravitational waves, which is a prediction of Einstein's theory 100 years ago.
In January of 2020, for the first time, researchers have confirmed the detection of a collision between a black hole and a neutron star. In fact, the scientists detected not one, but 2 such events occurring in just 10 days. Another example of events that could cause a gravitational wave is when a star explodes. This is known as a supernova. The tremendous amount of energy released during the explosion can generate enough curvature to cause gravitational waves.
Supernova in hundreds of galaxies have been measured, and we've made a map of the universe. We've got the distant galaxies, we know how far away they are, we know how fast they're receding. What happens? Well, a supernova in our galaxy happened on average once every 100 years. The most famous one happened in 1054 AD. It's called the Crab Nebula. You can see it with a small telescope in the sky. It's a beautiful cloud of expanding gas. So this is a star that's died and exploded. 1054 AD, it exploded. How do we know that? Because it was observed by Chinese astronomers, and this place, it's called Chaco Canyon, which is in the southwestern United States, very close to the border. There was a civilization here 1,000 years ago that built structures like this, enormous castles and houses in the desert. Now this was 6,000 light years away, which is a star a long way away from us. And with modern computer simulations, you can wind the sky back to see what it would have looked like on, I think it's July 4th, 1054 AD, when the supernova happened. So these people, 1,000 years ago, observed a new star shining brightly in the sky for 2 weeks, the Crab supernova explosion.
Gravitational waves carry information about their inception and about the fundamental properties of gravity that can't be seen through observations of the electromagnetic spectrum. Many models of the universe suggest that there was an inflationary epoch in the early history of the universe when space expanded by a larger factor in a very short amount of time. If this expansion was not symmetric in all directions, it may have emitted gravitational radiation detectable today as gravitational wave background. This background signal is too weak for any current operational gravitational wave detector to observe. However, LIGO is just the first step, and with future instruments we could potentially pick up gravitational waves that ripped through the first moments of the Big Bang that would solve one of the greatest mysteries in physics.
And inflationary cosmology suggests that before the Big Bang, which means before the universe was hot and dense, the universe was doing something else. And we have very good evidence from looking at the early universe and the structure, actually the distribution of galaxies in the universe today, that tell us the universe was doing something else before the Big Bang, are at least possible, if not close to being valid as and probably the standard model now, I would say. It's called inflationary expansion. So you've got this thing going on. It's the universe, just to give you the number, the universe is doubling in size every 10 to the minus 37 seconds. And it stops. And in stopping, the energy that was driving that exponential expansion gets dumped into the universe. It hits it like a at an instant, like ringing a bell, and sets off sound waves in the universe. And we can see those sound waves. And quite remarkably, it's like throwing pebbles into a pond. That theory also predicts that the universe doesn't all stop at once. In fact, it almost naturally predicts that the universe stops in a small patch and you get a big bang, and then the rest of it carries on and you get another small patch, you get another big bang, another small patch, you get another big bang, and it leads to this picture called the inflationary multiverse, where the suggestion is that there could be an infinite number of universes. And not only that, but the laws of nature can be different in every one, quite naturally. So you eliminate the need to worry about the fact this universe appears fine-tuned for life.
Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.
To the Mexican